next presentation is from Wenbin Liu from Stony Brook here. And he did some work about tuning communication libraries for A64FX.
Okay, so can everyone see my screen?
Yep.
Yes.
Yep.
Yeah. Okay. So I don't have any fancy application benchmarks, or hasn't actually reached the communication libraries yet. But this is just one simple benchmark and some interesting piece of knowledge I discovered about what compilers are doing behind the scenes. So I guess most of us have heard of this stream benchmark, which is a synthetic benchmark that measures sustained memory bandwidth for 4 different vector kernels. For the copy kernel, we're just in a loop, we copy a vector of doubles from one vector to another. And we also have the scale kernel, which multiplies one of the vectors with a scalar and then copy it to another one. We also have the sum and the triad kernels, but they are not the topic of our discussion today. So let's compile the stream benchmark with GCC 11.2 and with all the required optimizations, run it on Ookami. And here are the results. Note that, yes, for add and triad, both of them achieve better bandwidth because they have more data on the right-hand side of the equation. But for copy, notice that it is like 40% of the bandwidth when compared to scale. But if you look at it, the scale is actually doing more work. So why does a simple copy is actually slower than modifying it with a scalar and then copy it? Well, if we check the generated assembly with, let's just tell GCC to output the assembly code, you will see that GCC is trying to do something smart here. So for the copy loop, it actually replaced the entire loop with a single memcpy. And this actually caused the memcpy implementation in our glibc, which on Ookami is running CentOS 8.1. So it's glibc 2.28. I believe that was released like 4 years ago or something. And for the other kernel, the scaling kernel, you can see that it actually gets compiled using the Z registers, which are the SVE registers. We have load, we have we have multiplication, and then we have store. And so you can see that by replacing, the compiler is trying to do something smart, because on x86, we would expect the glibc to implement a multiple version of memory copy for different architectures if it sees as AVX instruction if you try to use AVX. But because glibc 2.28 doesn't have SVE optimized memory copy, the GCC is actually shooting itself in the foot by replacing it with memcpy. And that's why we get this worse performance. And to fix this, we can add fno built-in to the GCC compilation command line. And now we run it again, we can see that we have bring the copy loop to be the same performance as the scaling loop. So what happens for the other compilers? Well, for Clown 13, it doesn't, even using fno built-in doesn't help. We're seeing the result as bad as GCC, because Clown also tries to be smart and replace that loop with a memcpy, which uses the worst implementation. And for the latest Clown, which is Clown 15, the fno built-in works, and we can see that copy and scale loops are also having a similar performance. They're actually better than the GCC ones, but only slightly better. And for ARM Clown 21.1, we don't need fno built-in. It automatically generates SVE instructions instead of trying to be smart and use memcpy. And for Cray, we can see that it's even faster. And Fujitsu, again, generates the best code for this particular benchmark. And, but you may ask, okay, what if my code actually uses memcpy? Or it's C++ code, so I use studcopy or studcopy_n. Well, most compiler wouldn't dare to replace function calls because that's what the user tells it to do. It if it tries to be smart, then it may be again shooting itself in the foot. So again, we are stuck with glibc. And glibc, the latest release is 2.35. And I checked it, it still doesn't have SVE optimized memcpy. So if we're relying on glibc, then we will wait for years and years until we can get SVE optimized memcpy with the system. But in my experiments, ARM clone is actually the one exception. Even if I explicitly say to use memcpy, it will replace that memcpy with SVE instructions. The generated code is too long to show here, but you just have to trust me that ARM clone is being very smart here. It replaces the memcpy with faster SVE instructions. But for the other compilers, like Cray compilers and Fujitsu compilers, no luck. If you use memcpy, then you fall back to glibc and you have worse performance. Another solution is that, of course, you can write your own memcpy with SVE. There are lots of videos and articles online, and you can just write your own routine. It's not that complicated. I have provided a sample code at the end of this presentation. So if you're interested, you can try it in your application. It's a very simple drop-in replacement for the libc's memcpy. And about intranode communication, what's the impact of this? Well, if you're using MPI, remember that MPI supports shared memory transport for intranode communication. Even if you're not aware of it, you're just running two ranks on the same node. MPI will automatically use shared memory transports like CMA, KNAM, or XPMEM. But at the end of the day, they both call memcpy and they fall back to glibc, and it's slow. In fact, in my experiments, glibc's memcpy on A64FX is only about 8 gigabytes per second. And it's actually slower than internode RDMA writes. So it's slower than InfiniBand. So I know in many applications, people will assume that if two processes are running on the same node, then communication between them are going to be faster. And that's why MPI communicator can be splitted using shared memory type. But if you're using glibc, unfortunately, that is not true. If two processes are resting on the same node, they actually talk to each other slower than with InfiniBand. So what we're going to do here is that the communication libraries are still catching up with this. I have submitted a pull request to UCX to actually implement SVE-based memory copy. That has been merged, but they still need to actually use this optimized memcpy for different ISAs because they have this UCT layer that is quite complicated, and they need to have a unified infrastructure to select the best memcpy for different ISAs. For MPI, there was some work done by an intern at ARM in 2020. And they have published a paper called Using ARM Scalable Vector Extension to Optimize OpenMPI. That's not just memcpy. Also, they optimize the gather operations using SVE, which is pretty nice. But last time I checked, the repository has no activity since then, and probably has not merged upstream OpenMPI yet. And also, maybe you can try to compile your MPI implementation, or if you're using HPX, you can compile HPX with ARM clone just to see, well, ARM clone is smart, maybe it has replaced memcpy and other C library functions with SVE instructions. So the takeaway is that open source compilers like GCC and upstream clone could still do better in terms of SVE awareness. If you really have to use them, you can try the FNO built-in flag to see if that improves performance. But if you can, then you should try the vendor compilers and run benchmarks. Fujitsu and Cray compilers really do generate super performant code, and ARM clone is actually smarter in some cases. And as a last resort, you can of course use handwritten SVE routines to see if it does improve performance. And this is the sample code I was talking about. It's not that long. You can just use it as a drop-in replacement for SVE, for your libc memcpy, and include it in your code. And when you compile it with memcpy equals a64fx, this marker will be automatically defined and you can use this function. So this function is written by myself, it's in public domain, you can use it. But my disclaimer is that it will burn your house and kill your cat. So use it at your own risk. And that's it for my presentation. Any questions?
Thanks very much. How's your cat doing?
So I presume you could just call it memcpy and then use LD preload to insert that into your program?
Yeah, LD preload trait is another option, yes.
And then what data set sizes were you testing on? Because clearly, if you're working on data that's sitting in cache, then maybe using SVE instructions is critical.
The official guideline of the stream benchmark says you should use array sizes that are 4 times bigger than your last level cache, which is what I was using here.
Okay.
So yeah, it's working from the memory.
Okay. Well, I guess what I was getting at was to get full main memory bandwidth, it sounds like one still needs to be using SVE, that just plain old ARM instructions or maybe Neon won't deliver that. So that's interesting.
Mm-hmm. Yeah, and also these are just single core results. By using a single core, there's no way you can reach the full bandwidth because you're in a single CMG. Yeah. Okay.
Yeah, my experiments, I think single core maximum thread bandwidth is about 55.5
yeah, it's about
second.
this. Yes. Okay.